Since I equals C dV dt, the current will be a maximum when the rate of change of the voltage is greatest at the zero crossing. So the voltage, greatest rate of change of the, right there. The induced current reaches its max value a quarter cycle before the voltage does, meaning the current leads the voltage by 90 degrees in a capacitive circuit. Often this is remembered using the mnemonic ICE, I-C-E, where the letters stand for current, capacitor, and voltage. I, current, C, capacitor, E, electromotive force, kind of an old term for voltage. And what that says is that current leads voltage, and a capacitor, you just have to remember that it's a quarter cycle or 90 degrees. In this context, capacitance can be taken to mean the ratio of the current flow through a capacitor to the rate of change of the voltage that caused the current to flow. Here it's the voltage that appears in terms of the rate of change with respect to time, and the capacitance instead is the proportionality constant linking it to the current, I. You notice it looks just like V equals L di dt. It looks just like V equals IR. They're all kind of versions of Ohm's law. It's just for capacitance. The rate of the constant of proportionality C is the, you could think of it as C equals I over dV dt. The rate, we would say the ratio of current, of induced current to the rate of change of the voltage that induced it. And so again, it's analogous to Ohm's law and is a linear function just like Ohm's law is. From this graph here, we see that current is a maximum through the capacitor when the rate of change of voltage is at a maximum, and the current is at a zero when the rate of change of the voltage is zero. So rate of change, again, rate of change is a maximum here, here, and here at the zero crossings, and simultaneously the current reaches its peaks at that point. The rate of change of voltage is zero here and here, and at both of those points the current went to zero, fulfilling that I equals C dV dt. Although we use parallel plates to represent the concept of capacitance, the same property of capacitance can be exhibited by other devices. For example, transmission and distribution lines in the power system have capacitive properties between them and the ground, the physical ground, the earth, I mean. The overall impeding effect of capacitance on a circuit is expressed by a reactance called capacitive reactance, and not too surprisingly, it's given capital X sub C is its symbol. It's also measured in, man, that's a bad ohm, but that is an ohm symbol, measured in ohms. It's the inverse of the product of the angular frequency and the capacitance. So X sub C is equal to negative 1 over omega C. That's equal to negative 1 over 2 pi f times C. So here we see that at high frequency, the voltage across the capacitor is going to change rapidly, easily passing current, and therefore the less the impeding effect, right? So if omega is high, we know that voltage across the place is oscillating quickly, current can easily flow, the impeding effect is small. If omega in this equation is high, X sub C is going to be little. At DC, or at low frequency, the lower the value, the capacitor is going to behave more and more like an open circuit. As it gets to DC, it's actually essentially going to behave like an open circuit. The smaller omega gets, the bigger this value gets. So as the voltage remains constant, no current can flow. Therefore, the capacitor acts as a large impediment to AC flow at low frequencies, and we can see that because the capacitive reactance gets big. So a capacitor is therefore an open circuit to DC. We'll see that sometimes the circuit elements, capacitors, are therefore used to block DC levels and low frequency AC, and are used to pass high frequency A signals, so we can use them as high pass filters. You'll also notice that there's a negative sign in this one that we haven't accounted for yet. The purpose of the negative sign is that the reactance created by capacitors will cancel out with the reactance created by inductors. So if I have 5 ohms of reactance created by an inductor, it is actually opposite type of reactance as created by 5 ohms of capacitance, and they'll cancel each other out, if they're in series that is, to form 0 ohms of reactance. So we indicate that kind of arbitrarily. We chose that inductive reactance will be given a positive value and capacitive reactance will be given a negative value. There isn't actually anything negative about the type of reactance. It's just different than the type of reactance produced by inductors and therefore needed to cancel mathematically. That's with a negative sign. So that's why the capacitor gets the negative. So that standard is across all of ECE, all of ECET, all of engineering and engineering technology. Capacitive reactance is by definition negative reactance. Capacitive reactance is in the electric power system is most often formed between transmission lines in the earth or in capacitors that have intentionally been inserted into the system to purposely cancel out the effects of the inductant reactance of motor loads and such things.